Okay, ladies and gentlemen, also warm welcome from my side. My name is Robert Tikovsky. I'm Executive Vice President in Linde for the product line Hydrogen Syngas. I was working a long time in project execution as a project manager. Myself, I built 2 ammonia plants based on in China actually, based on heavy hydrocarbons, partial oxidations, front-end syngas generation. We heard that ammonia has its hazards, its risks, but I can tell you that the risk already starts much earlier with building the plant. It's of course only monetary risk, but it's a risky business. I would like to talk with you today about the state-of-the-art ammonia plants. And I put also global project execution capabilities, because state-of-the-art ammonia, I think all of you immediately would think about, if you hear state-of-the-art, you think about probably technology. But it's technology definitely, best technology definitely is the basis. However, there is a lot more to it, like a good technical concept, and in the end, the ability to execute such a project nowadays in a global environment in various geographies. But a short introduction about Linde is very quick, just to give you an idea what Linde is about. The Linde Group is mainly an industrial gas company with an engineering division. The revenue, total revenue of the group is about 18 billion, whereas the revenue of gases is more than 15 billion, and Linde Engineering is only 2.5 billion, about this range. So you see, we are I'm from Linde Engineering, so the plant building engineer. So we are the small division of Linde Gas. Why is it this integrated gas and engineering business? Why is it a success model? We think it is a success model because of the synergies. You have here, you have Linde Gas on one side as a plant operator, exposed to the competition, very competitive in the market, and on the other hand, you have here Linde Engineering bringing the technology, bringing the competence to execute the plants. And we have, of course, we are able to tap into the operating experience of our big brother or sister, Linde Gas. So Linde Gas has hundreds of plants in operation. And of course, this is a huge source for us, this data source where we can tap in and take solutions and input for our engineering business. Now, it's not only about producing gas, industrial gases, all kind of gases, air gases, then gases from hydrocarbon, rare gases, specialty gases, gases about healthcare. It's the whole span of the value chain from the gases to the gas applications, which Linde does and Linde Gas is doing. And you can see here the applications are in all kind of industries. This is health, metallurgy, petrochemical, and so on and so forth. And we have, Linde Gas has special department who is permanently and continuously looking and working with the customer to find applications for industrial gases in order to improve the manufacturing process of the customer. And these machines, these apparatus, in order to apply these gases, is also part of our business. Now let's talk a little bit about Linde Engineering, actually where I'm coming from. We have in Linde Engineering 4 major product lines. This is air separation. Gideon mentioned it in the beginning. This is actually where we're coming from. The Professor Dr. Karl from Linde, he invented the cryogenic process for separating the air gases. Then we have hydrogen and syngas. This is where I'm coming from, as the name is saying, mainly hydrogen, but all kind of syngas applications, gas conditioning, and ammonia is also part of it. Natural gas, our natural gas group, and this is petrochemical, hard to see it, but and then our natural gas division doing all kind of gas processing plants, natural gas to liquid, natural gas liquefaction, and so on and so forth. We are holding a lot of patents, and we can look into about 4,000 executed projects over the time of our existence. Now, what is the speciality on us as an EPC company? EPC, for those who are not familiar with this expression, it's engineering, procurement, construction, meaning a general contractor for building plants. What we can, what we are proud about is, what we can say is we are not only an EPC company, we are also a technology EPC company. A lot of technologies, a lot of plants we are building, the technologies for that we are owning ourselves. Where we don't own it and we have to find an integrated solution for a huge application, we have access to a licensed technology, and we are open to work with each and every licensor. You will see a few examples later on. Now, let's come back to our topic today, state-of-the-art ammonia plants. And this is more or less the roadmap to it. First of all, of course, there stands the technology. As I said, this is the basis, and we think that for certain applications, in particular for a certain range, certain capacity of plants, we have really the sweet spot here with our technology. The Linde, it's the so-called Linde ammonia concept, and I will elaborate a little bit more about it in a few minutes. And then, of course, there is the technical concept. And here we talk, what is very important here is with the standardization, and hand in hand with standardization often goes modularization, because this is something which gives a very competitive edge in our market today. We have to be continuously looking for methods to stay competitive and cost efficient, and I would like also to elaborate a little bit more about why we do modularization, and finally what means project execution in nowadays environment. And the whole thing could be subtitled with cost efficient, cost effective and competitive ammonia plants. Why did I put small scale in brackets there? Because, as I said, in particular on the small scale plants, the capex portion of it, the smaller the plant gets, the capex portion of it gets over proportional, and in particular for these smaller scale plants, it is very important to find competitive and cost efficient solutions, and also processes how to execute and build. Okay, let's have a look on the Linde ammonia process. Here, a comparison between a conventional process. I think it's, to a conventional process. I think it's quite evident. Our process is much leaner, much less process units. In particular, in principle, our Linde ammonia process is consisting of a hydrogen plant and a high efficient ammonia synthesis. It's a steam reformer, isothermal shift, and a PSA, Whereas the conventional process here, you have the gas generation step is divided already in two steps, normally primary and then autothermal reformer. Then you have, instead of the isothermal shift, you have here low temperature and high temperature shift. And then you have here the methanation step at the CO2 removal. These are three catalytic steps here, which we don't need in our process. This immediately means 50% less catalyst. And of course, catalyst is cost, is maintenance, and so on and so forth. Then another nice feature here is the CO2 removal is not compulsory, because the PSA also takes out the CO2. So the process itself, it's much slimmer, and a very important feature, we bring together the hydrogen and the nitrogen exactly at the point where it's needed, just upfront or upstream the synthesis loop. Meaning the whole route, of course, has less flow compared to conventional technology. We have less inert gas. We don't have inert gas. It is excess air. What you carry here through the whole route, you don't have it here. This means advantage in equipment sizing, in pipeline sizing, of course, a pressure drop. I think we come to that summary later on again. Well, now I think I have to step down a little bit because I thought I have a I got the monitor here. Well, the main characteristics, in principle, I said it already. It's an inert-free ammonia synthesis gas. The advantage is we can adjust the CO2 and the ammonia ratio according to the requirements, dependent if you want to have maybe a CO2 byproduct or whatsoever. It's a very flexible process with respect to feedstock. We can go from very light natural gas feedstock to heavy feedstock like vacuum residual or pitch, for example. And it is very flexible with respect to byproducts, what I want to have. I mean, you see it here. We have here the air separation unit. Of course, the air separation unit here does not only produce nitrogen. We can only have, or the client, if needed, can only use the oxygen, which is anyway a co-product here. Or we can amend it and the cold box in order to produce some rare gases. So very flexible. Then on the hydrogen side, out of the PSA, you get the purest hydrogen you can get, 99.99999 5 times 9. So you can, if you need, you take off the pure hydrogen there directly, and then of course CO2 can be used as a byproduct, or again nitrogen if you need certain some nitrogen for utilities. Now, with respect to flexibility in plant design, again, CO2 removal, yes, if it's needed. For example, for if the client would desire a urea full conversion to urea, we can extract the CO2 and then route it to the urea unit. Pure hydrogen, pure nitrogen, as desired. I said this already. This is in principle a repetition of what I already said. The gas purification system, PSA, in our standard hydrogen plant has this additional advantage that you could even run the ammonia plant without the isothermal shift, because the PSA also can take out the CO. And of course, all these features have an impact or an effect on cost and energy saving. As I said right in the beginning, the elimination of 3 catalytic process steps give you the advantage that you need less catalyst, about 50% less. This has consequences then, of course, on maintenance, refills, and so on. The slimmer design of the equipment and the piping, due to the fact that we bring the ammonia, the nitrogen and the hydrogen together just in front of the ammonia synthesis. Less pressure drop, less energy also for the synthesis gas loop. This is the dimensioning of the machinery is much slimmer as for a conventional plant. And as a summary, the Linde ammonia concept is the much more direct route to ammonia. So there are savings, the process is very flexible, and of course you have less equipment, less catalyst and so on. This increases definitely the reliability. Now to give you an overview about the whole family of this process, as I said, we have a huge variety, or we can use it for a huge variety of feedstocks, light feedstock to very heavy feedstock. This L1 process means light 1. This abbreviation is the one we have talked about now. Then there is the so-called L2 process. If you, for example, want to go to full conversion to urea, or conversion to urea, there is the CO2 extraction, and there is a second catalytic or non-catalytic step for single generation. Then the so-called LAC3 process. This is in principle just cleaning of hydrogen-rich off-gas. This hydrogen-rich off-gas can come from any stream in the refinery, for example, or methanol plant off-gas. This gets cleaned up, for example, by a PSA, and then it goes into the hydrogen together with nitrogen again, goes into the synthesis. Last but not least, there is the variation with the heavy hydrocarbons. Here we are typically, as a syngas generation, we are typically with Linde using a partial oxidation unit where we gasify, for example, vacuum residual or pitch, or even coal, of course. Then a sour shift, a CO2 removal again, and instead of PSA, you have here a nitrogen wash unit, meaning this in principle is a cryogenic cleaning and takes out the rest of the methane and the impurities, and adjusts the nitrogen to hydrogen ratio. Now, to visualize a little bit these various process steps, these here are all Linde-owned technologies. Air separation, as we already said, this is where we are coming from, Linde. Then the steam reforming technology is also our own technology, and applied hundreds of times already in, for example, also hydrogen plants. Then Rectisol wash process is a CO2 removal step, which is typically used in this LAC-H process, meaning for heavy hydrocarbons, where you have due to various reasons, but one reason is the pressure level. You have a partial oxidation unit as a front end, which is operating at for this kind of feedstock maybe at 80 bars or so, and then in the back end, the Rectisol wash unit is the more adequate process step compared to an amine wash, which we see later on. Here, a pressure swing adsorption, also our own technology. Then we have here isothermal shift conversion. This is also Linde proprietary equipment. It is in principle, it is actually, let's say, how can you say, this does everything. It's a heat exchanger, it's a reactor, it has a multiple use. Sometimes it's used as a reactor, sometimes as a heat exchanger. It's a spiral wound heat exchanger with 3, 4, 5, 6 passes. Very, very flexible, very high variety of applications. And for this kind of process, we use it as internal or the medium pressure steam for the process is also generated in there. So it's completely integrated, also compared to the conventional process where we have, if you remember, the low temperature and the high temperature shift. Normally in between the two process steps, you have a cooling chain. This is completely eliminated here because it's also integrated in this one and single slim equipment. Then catalytic oxidation in case of this full conversion, this L2 process. This is something like an ATR, also our own technology. Nitrogen wash unit. This is where we're coming from cryogenic processes. And as I said in the beginning, where we don't have our own technologies, we have access to licensed technology. For example, for a partial oxidation, usually we go with the GE, but it could also be somebody else. For the ammonia synthesis, we have worked with Casale, we have worked with Topsøe. We are also open to that. And for the amine wash system, usually also there we can take whatever is and we have worked with whomever is on the market. Now, this is a nice example of a plant which recently went in operation. It's a plant in the Middle East operated by Linde Gas. It's our own plant, and it's a poly-product plant, as you can see. 130,000 normal cubic meter of syngas is generated there. Products are CO2, hydrogen, and ammonia. And this is, as I said already, where we see that our process has certain advantages because you can integrate it, and you have, in particular, where you need a variety of poly product application, there we have this flexibility. This plant you will see later on again. This plant here is stick built, and it has been stick built in the end. I come to that later. Here a nice picture of it. On the right hand side you see all these units what we were talking about before. This is on the right hand side. In principle you have the syngas generation, and here you have the ammonia side of it, the ammonia loop, ammonia reactor, the ammonia synthesis, and the refrigeration, and here the machine house. Whereas here you have the two big steam reformers you see here, then the two cold boxes of the nitrogen wash unit, the towers of the amine wash. This is the SMR cooling chain, so this is where the syngas is cooled down. And here the PSA, you see here just the very tall PSA buffer vessels for the PSA purge gas. Now, when it comes to standardization, as I said, the main feature of our process is, or let's say the core of this process is a hydrogen plant. And when it comes to this smaller scale ammonia plant, standardization is an issue. And since we also play in hydrogen, we have developed over the years a nice portfolio of completely standardized and modularized hydrogen plants. Standardized meaning, of course, using always same features, same maybe also same vendors, same parts. This means you can shorten and cut back all the procurement process. This allows you to be more more concise and faster in engineering. Here on the very left-hand side, this is the smallest of this family, the so-called hydroprime min. It's practically a containerized hydrogen plant going into a 40-foot container up to capacity of 300, 330 normal cubic meters. This is off-the-shelf, an off-the-shelf equipment. Then beyond the 300, 500 normal cubic meter, we have this, out of this family, so-called hydroprime mid. I don't like very much the names, but they somehow were established, and we could not change it again or anymore. These are small, modularized, highly modularized hydrogen plants. The complete cooling down train is, you will see later on, in nicely modularized. And for syngas generation, these are can reformers, can type, these tins. We use 1 or 2, depending on the size of the plant. Capacity range, as I said, from 600 to about 15,000, 16,000 normal cubic meter. Whereas you can go with one can maybe up to 6,000, 7,000 normal cubic. Then the next one is so-called hydroprime max. This is actually a recent development. We put a lot of effort over the last 2 years in development of this unit. It's, of course, from technological point of view, it's not a new development. But to really standardize it and modularize it, this was an effort. I will elaborate a little bit more just in a few minutes. Well, and then the more you come to the right-hand side, the more the plants become customized and bigger. Now, if we talk about small ammonia plants in the range of 150 to 350 metric tons per day, this hashed area here, this would be the application, the ideal application for this kind of standardized hydrogen plant, as which would serve as a core unit for these ammonia units. Now, this is a typical arrangement here. On the lower end or on the upper end here, you have either can or box reformer with a waste heat recovery system. So all this here down this is a horizontal waste heat recovery. The reformer you see here, this is a can type. Then this is the cooling structure, arrangement of heat exchangers where the syngas gets cooled down, and then here you have the syngas cleaning by a PSA unit. And all these are our technologies. Now, this is the hydroprime mid. This is this can reformer type. You see here the can reformer. Here in the picture we have 2 of it. The syngas comes out on the top and then goes into one common header. The whole thing is bottom fired. Has its advantages because it's easy accessible. You can maintain the burners very easily. It's easy to control and has a low investment cost. Now this is the bigger brother, this hydroprime max, and the major effort, as I said before, was really completely modularizing this reformer. Here, it is a one-row concept. So this reformer has only 1 row, but we are flexible on the harps. You see here 1, 2, 3, 4, 5, 6 harps. Usually, we would use this kind of reformer starting with a capacity of around 16,000 normal cubic meter, a 3-harp type, and then stepwise going up to 48, 60, 72 tubes in order to increase the capacities up to 28,000. And you see here the box completely, these are 1, 2, 3, 4, 5 horizontal modules, the penthouse modules, already with burners, piping, burner control system, everything installed. And here, the waste heat recovery system, where the flue gas leaves the reformer box. In this case, it is a vertical waste heat recovery. It goes up, and then on top there is the stack. Also, these various bundles, steam generation, feed superheating, whatsoever is in here, are completely modularized, come completely modularized with refractory, everything already in, which on site you just have to put it one on top of the other. Okay, this again, now coming back to the picture you saw before. You remember this Sadara Al-Jubail plant, this Linde gas plant. This was originally, the concept of it was originally modularized. Finally, then in the end, the plan changed and it became a stick-built plant. And why? We come to that now because I would like to talk with you a little bit about modularization and why we do that. There are certain drivers. In principle, modularization is nothing else than de-risking. We want to de-risk the project. Now, risk is money. If you have a lot of risk, you have to evaluate the risk, and this risk goes into the cost of the plant. So in the end, modularization must pay off in the overall. It must pay off. The whole project must get cheaper. So it's about cost reduction. It's about schedule attainment. But also schedule is, of course, money in the end. And it's about HSE, safety. What are the criteria? On the labor side is, do we have, for example, on a construction site in the desert, in Siberia, whatsoever, do we have access to skilled labor? And this, for example, was then the driver, or let's say the switch, or the kick why we switched for this Al-Jubail plant to the decision stick built, because in the end certain other projects did not realize in that area, and suddenly there was a lot of cheap and skilled labor available. So in the end it was cheaper, more cost efficient to build it on site than to do it off-site and modularized. Why? I come later to that, because there is a certain trade-off, of course, with modularization. Skilled labor is an issue. Cost of labor is an issue. Of course, if you have to bring skilled labor to Siberia, the allowance, then reduced working times and so on and so forth, you have a lot of inefficiency in there. And on the environmental side, of course, in a yard or in a workshop, you have a much more controlled environment than on a bumpy site. Construction site, you're not exposed to the weather conditions as it is in a workshop. You get out better quality, safety. You can control this aspect much better. Already the ground and the floor. Pardon me?
You are limited with the size you can do inside the workshop.
Of course, but you will, I come to that, you will see a certain, you are limited, depends. We do modules up to 4,000 tons. So you see that. Yeah, and another advantage with regard to schedule, you can do kickoff fabrication, modularization, installation in parallel to the site works, of course, and certain pre-commissioning activities in the end also can be already done in the yard or in the workshop. Now, as I said before, certain trade-offs you have, of course. You have, in the first place, with modularization and prefabrication, additional expenditures for transport, because of you have to investigate the whole transport route. You have bigger modules. The transport costs more because of the module size. You might have maybe there has to be accompanied. And in the end, you also put more steel because you have to You have to provide for the static and so on, for transport movements. This is a nice example regarding steel. You see here the left-hand side is a stick build, the right-hand side is a modularized, so you have to put much more steel in there. Now, what is in this respect the advantage of a technology EPC? We can, of course, we start in the very front and in the process design already with view to modularization if we decide to modularize, and we can design the equipment accordingly. This is it's not very nicely to see, but this is a very cumbersome equipment, a deaerator here, which is a T-shape equipment. On the stick build version, very hard to install. We have the ability to design it differently, for example, as a vertical vessel here, which just goes aside the module and will be put on site separately. This is an example just to demonstrate to you that we have various concepts in place for pipe racks, for process units, for super modules in the drawer, which we then apply when it comes to the specific project. Here an example, because you say limited in size, you can also, of course, also do an offsite installation. This was a site, offsite, our construction site, where we built these furnaces. These were 5 furnaces, each one 2,600 tons, in an exchange of 12 old furnaces. So we built this offsite, and then within 30 days, we exchanged all the old furnaces by the new furnaces. And on top of that, even more complicated, you can imagine 5 furnaces don't fit on the foundation of 12 furnaces. So you also have to exchange the foundations, and also the foundations here were prefabricated, precasted offsite and then put in. And the whole thing, 5 of these furnaces was done in 30 days without any day of delay. Well, this is one of our flagship projects. I will hash through it now. It's only examples. This is a LNG plant north of the polar circle in Norway. The whole plant was modularized and prefabricated all over the world and then shipped to the site in various conditions. This was, for example, a cold box roll-on, roll-off. You see these multi-wheelers here underneath. Where is it? Here, these multi-wheelers, they drive on the ship and then drive off the ship, of the barge again. The process modules here, this was a gravity-based structure down there. This was a kind of a ponton, which was lifted up. The plant was built on this ponton. And then at the arrival, there was a excaved space here where this ponton went in, and then it was flooded and tied to the ground. So as I said, the whole plant modularized. Here you see the slug catcher, everything, each and single unit, single process unit came in from a different part of the world, and finally was assembled in this harsh environment. So the purpose was, or the problem was there, very harsh environmental conditions, very hard to work there, therefore extreme modularization. This is another example. This is a basic engineering only, was never built by us, but a complete LNG plant, floating LNG plant on a ship. Another one of super modules, again, okay. Now, when it comes to project execution, this kind of project, these examples, what you saw here, of course, you have to have the capabilities to execute this kind of projects. It is not easy. You have, you go into very harsh environment. You source your equipment and build all over the globe, depending on various criteria. So you have to have a very strong project execution team. And organization, this is what we have. It's a centralized organization in Linde, and all the other departments like engineering, procurement, and the product lines are servicing this department, assigning the personnel to it. Just to give you an overview about our execution hubs, the black dots are all execution hubs all over the world where we do engineering or fabrication, specialty equipment like, for example, the spiral wound heat exchanger, cold boxes, and so on. We manufacture ourselves, and in China as well as in Germany. And as I said, organization is a must. You have to have a global setup in nowadays. Normally, you have to also have global engineering hubs due to low cost and cost efficiency. There is almost no client anymore nowadays who is willing to pay $150, for example, for an engineering hour, even though it's German. So we also have our subsidiary in India with about 1,000 people. Then clearly structured processes. This is definitely something you can imagine where so many parties play together. Things have to be defined quite accurately. We have our integrated management system where these things are laid down. We have, when we work with our subsidiaries, predefined work splits dependent on the product, on the plant, on the location where we go. With the work splits also come the definition of the responsibilities and a very structured change management. This is very important not only towards the client, but also internally, because you can imagine if somebody in Munich changes something and his colleague in India has to pick up the work, he has to know what the other guy was doing. Competence in execution, I just want to say one thing. Project managers, of course, are the key to the success. They have to be strong, they have to know the organization. We have a lot of top project managers who were grown in the organization over decades. And then you need, in nowadays, the right tools. And this is something I will come to that right in a minute. And with the tools, you have to have the processes with standard gate reviews where you continuously, along the way of engineering project execution, can control schedule and quality of the project. Last but not least, of course, the references of already installed plants. Here just example of such a phase gate model throughout all the phases of the lifetime of such an EPC project, from sales phase to execution phase. And all these intermediate milestones are review steps where we apply certain state-of-the-art tools, design tools, of course, review tools. And one of our latest tools which we are applying and developing is virtual reality, where we have the possibility to do operator training for the client in a virtual plant without having the risk of getting the plant damaged, without having the risk to expose people to certain hazards. And this is what I would like to show in a small video. You would have to click on.
How long is the video?
2 minutes.
2 minutes? Okay.
On the last, if you click on the last icon here, right. And you have later on the opportunity to have a look to this virtual world outside in our booth with the goggles and so on. Here, yes. No sound. No sound. No sound. Okay, maybe then it's better, but then you have to go one after the other. You have a look and you make your own experience afterwards during the coffee break or along these 2 days into this booth just opposite of this room. Thank you very much.
Thank you.